right, so the next problem on the review that we're going to do is going to be the integral from negative infinity to 0 of e to the minus, now in parentheses, w over the square root of 8 squared dw. So again, I just want to note these problems, right? So the whole reason that we use the normal table is because we cannot evaluate this integral. This integral does not have a closed form expression for it. We use the normal tables. We use the normal tables to calculate probabilities precisely because we cannot integrate this. What we're doing here is we're using the fact, right, that the integral from negative infinity to infinity of the density function, any density function, is equal to 1, right? We're not directly integrating this. If you try to do that, you will not be able to. So I just want to emphasize that. Anyways, so again, just like in the previous two problems, we want to compare the inside of this. So compare to normal random variables, probability density function, right? So again, like I have said, if we have a random variable x that is normal with mean mu and standard deviation sigma, then the probability density function, little f of x, is going to be given by 1 over sigma times the square root of 2 pi times e to the minus x minus mu squared over 2 sigma squared. So this is the density function that we want to manipulate this expression here to look something like that. Right, so let's do that. So the first thing we note is we have this minus, and then the numerator and the denominator are being squared right now. Here we want to separate it out, right, and then we can kind of go from there. So the first thing we want to do, this is equal to the integral from negative infinity to 0. And now I'm going to square the numerator, I'm going to square the denominator. So this is going to be this is going to be e to the minus, in the numerator I'm going to have w squared. And this is going to be over square root of 8 squared, which is 8. And this is dw. Right, so this is actually pretty close to what we need here. What is the mean in this case? The mean is going to be 0, because this is the same, right, as minus w minus 0 squared, if you really wanted to do that. So our mean is going to be 0, and now we want to set this denominator again equal to the 2 sigma squared. So let's do that. So let's set 8 equal to 2 sigma squared. We divide by 2, so we get sigma squared equals 4. So sigma is going to be equal to the square root of 4, which is 2. So now what is the expression that we need to add here, right? We need to add this right here, right? Because we need this to be a density function. So in our case, 1 over sigma times the square root of 2 pi. Right, our sigma is 2, so this is going to be 1 over 2 times the square root of 2 pi. So, I'm not sure why I'm drawing another arrow, but that is okay. So now this is equal to the integral from negative infinity to 0. So in the denominator, I want to add this 2 times the square root of 2 pi. But again, I can't just divide by 2 times the square root of 2 pi. That's going to change the expression. So I also need to multiply by 2 times the square root of 2 pi. So I'm cleverly multiplying by 1. That's kind of how you think about this. And then this is e, and I'll rewrite this just to kind of emphasize the point here. And this is minus w minus 0 squared over, so 8 is going to be 2 times 4, right? And then this is, we're integrating with respect to w. So now, again, I want to pull this out of the expression because I want this inside to look exactly like a density function. So not look like, I want it to be a density function. So this is, and look like, I guess. So this is 2 times the square root of 2 pi. And now I'm integrating from negative infinity to 0. 1 over 2 times the square root of 2 pi. And then this is, I'll leave it in this form. So e to the minus w minus 0 squared over 2 times 4 dw. So now this, by construction again, we made it look like that, right, is going to be the probability density function of a normal random variable with mean, which is mu, equal to 0, and standard deviation sigma equal to 2. So now, but now I'm not integrating from negative infinity to infinity. If I was doing that, this would be exactly equal to 1. So now again, I need to use the symmetry of the normal PDF. So in this case, my mean is 0. So if I integrated from negative infinity to infinity, it would be exactly corresponding to the area under this curve. If I integrate from negative infinity to 0, that's corresponding to this area under the curve. But because of the symmetry of the graph, this area here and this area over here are exactly equal. So I'm adding up 2 equal things, and they have to equal 1. So that means each of them have to be 1/2. So now we get that this is equal to 2 times the square root of 2 pi, and then this integral becomes exactly 1/2. So now the 2 and the 1/2 are going to cancel. This is exactly equal to the square root of 2 pi. Again, I really enjoy this method because it allows you to calculate these integrals without actually integrating. It's just comparing them to a density function that you know what it looks like, and adding the right constants and kind of manipulating the expression to look the way you want it to. And then when you pull out the constants, that's gonna kind of be the value of the integral. So that's kind of nice. So anyways, that is it for the third video, and I hope you found that helpful. So